Hey everyone, welcome to the last class of Nets 412. I'm gonna unmute you all just for a second so we can all say hi. Hey everybody.
Hi.
Hello.
Hi.
Hello.
Good to hear everyone one last time. So just as last class we talked about differential privacy and its connections with game theory, I want to finish off the class by talking about an important contemporary topic, algorithmic fairness, and how it's connected to some of the game theoretic reasoning that we've been learning about in this class. So again, the primary thrust of the field of algorithmic fairness is not game theoretic, but there are certainly ways in which game theoretic models can inform its study, and that's what I want to talk about today. So just to give you some background, as many of you are aware, machine learning has really become a big deal in the last 5 to 10 years. And it's not that machine learning is new. We've used machine learning even sort of, not just as an academic curiosity, but we've used machine learning as an important industrial tool for decades now. But up until about maybe 10 years ago, the primary use cases for machine learning were for relatively mundane things whose outcomes were sort of low stakes. So things like maybe spam filtering or targeted advertising. Okay. Now, we still use machine learning for those things, but we're increasingly using machine learning to make high stakes decisions about people. So for example, when you apply for a credit card, your application might never be seen by a human being. You might just be vetted by an automated algorithm that will decide to give you credit or not. If you submit your resume to a big company like Amazon or Google, they get lots of resumes, and the first stage of screening might be an automated resume screening tool, again, driven by machine learning. HR departments at big companies, if you end up actually being hired, make compensation and firing decisions as a function of recommendations, again, that are sort of machine learning driven. And maybe sort of most surprisingly, if you haven't been following this area, criminal justice decisions are now increasingly made using automated algorithms. So if you are up for bail or parole in a number of states, including Pennsylvania, although it's a human judge ultimately making the decision, their judgment will be informed by the output of a machine learning model that tries to predict if you are released, whether you will go on to commit another crime or not. We'll talk about that a bit in this class. And this is all to say that because we are making sort of increasingly high stakes decisions with these automated decision-making techniques, there are concerns that technologies like machine learning might be either exacerbating existing human biases, picking up on patterns that are in the data that we wish weren't, or maybe even introducing their own. And so if you've been paying attention to the popular media, in the last, say, 5 years, you've probably seen article after article that kind of look like this, that are worrying, not without reason, that these machine learning algorithms are in some kind of inscrutable way, since we don't have great visibility into how they operate, are introducing or perpetuating biases in ways that are unacceptable given the high stakes decision making that we're using them for. Okay, so that's to set the stage. And this last article here, this article with the headline "Machine Bias" was an article in ProPublica that actually serves as a good use case, a good case study to sort of think about some of the complexities in this area. And so let me walk you through a slightly simplified cartoon version of what this article is about. So ProPublica was doing an expose on a tool called COMPAS. And it was a recidivism prediction tool. So this was a tool used by a number of jurisdictions that ProPublica was studying Broward County, Florida. And it was a tool designed to predict whether an inmate, if released, would go on to reoffend or not. So this was a tool used by judges when setting parole. You know, should someone who's up for parole actually be released or not? And you know, one relevant thing in making that decision is whether if they're released, they'll go on to commit another violent crime or not. And so that's what this tool was trying to do. It was trying to predict whether someone would reoffend or not. Okay. So the way in which what I'm going to describe is a slightly simplified version of what actually happened is the COMPAS risk tool tried to actually produce a score. It tried to predict your risk of reoffending. And in this discussion, just to simplify things, I'm going to imagine that it's actually just producing like a binary prediction, that it predicts that you're going to reoffend or not. Okay, so people have features. The tool can make predictions based on those features, and after the fact, at least, you can gather data on some of the actual outcomes. At least for the people who were released, you can look and see whether they did reoffend within 18 months or not, and so you can try to figure out where the COMPAS risk tool is making its mistakes. And so that's what ProPublica did through a Freedom of Information Act request. They gathered a bunch of data, both about the predictions that COMPAS made for particular inmates, and then for the ones who were released, whether those predictions were correct or not, whether they actually went on to reoffend or not. And what they found, and what was sort of the main thrust of their article, was that the COMPAS risk tool was unfair. Okay, well, they found something technical. So what does it mean to say that the COMPAS risk tool was unfair? Well, what they meant specifically was that if you looked at the false positive rate, right, the rate at which the tool incorrectly predicted that people would reoffend. So these are people who, in fact, according to the ground truth, did not go on to reoffend, but the tool predicted that they would. So the tool made, this is the rate at which the tool made mistakes in what is the harmful direction, right? Because if we predict that you're going to reoffend, well, that makes it more likely that you're not released. So this is sort of the direction in which the tool might make a mistake that is harmful to you. What ProPublica found was that the COMPAS risk tool had a much higher false positive rate on the Black population compared to the white population. So, you know, if I pick a random Black inmate who, in fact, was not going to go on to reoffend, and I pick a random white inmate who, in fact, was not going to go on to reoffend, the COMPAS risk tool was significantly more likely to mistakenly label the Black inmate as someone who was going to go on to reoffend compared to the white inmate. And they reasonably said that, yeah, this was unfair. Okay, now, North Point, the company that made the COMPAS risk tool, they've subsequently changed their name. I think that's not a coincidence, but they wrote a reasonably compelling response. They said, well, you know, actually, our risk tool is fair. You guys are just measuring the wrong statistic. And what we mean when we say that the risk tool is fair is that it has equal positive predictive value on both the Black and the white population. Now that means something different. That means that amongst all of the people, people that the tool predicted as being high risk, the same fraction of them, in fact, went on to commit crimes, whether or not they were Black or they were white. So what North Point meant was that the statistical signal that their tool produced was unbiased in the sense that it had the same statistical meaning for Black inmates and for white inmates. Again, that's something you would reasonably want. Bad things would happen if your signals meant different things as a function of the race of the inmate. Okay. And so, you know, this got a lot of people thinking, like, you know, on the one hand, it seems really bad to have very different false positive rates for Black and white people. On the other hand, it seems good to have equal statistical meaning for the signals that you're producing, independent of race, maybe what's going on is, we want like both of these conditions. Like maybe whatever fair means, it should encompass both equal false positive rates and equal positive predictive value. And just to sort of mathematize things a bit, what was going on here was that ProPublica and North Point had different formalizations for what they meant by fair, but they were both definitions in sort of the same style. Okay, so both of them proposed that there should be some collection of protected groups, in this case broken down by race. So, in this case, maybe there's just two groups, white people and black people. And ProPublica implicitly said, okay, well, a classifier is fair if for every pair of groups, the false positive rate is equal, meaning that if I look at all of the people who did not go on to commit crimes, all of the people who did not recidivate, that the fraction of people who were incorrectly predicted to be recidivism risks should be the same no matter what group you come from. Okay, so this was the ProPublica notion of fairness, or at least they were asserting that if your classifier doesn't satisfy this property, then you are unfair. And this is actually quite reasonable. We'll talk about in a moment why you might want this condition. North Point made a very similar proposal, right? Like if you look at these two equations, they're almost the same. It's just we're swapping the role of two of the variables. North Point proposed that a classifier was fair if the positive predictive value was the same, independent of what group you were a member of. Meaning, if I look at all of the people for whom the classifier predicted that they were going to reoffend, so if I condition on the classifier predicting that you are going to reoffend, then the fraction of people who actually do go on to reoffend should be the same, independent of what your group is. So this is saying, okay, well, the statistical meaning of the classifier signal, right? Like what you can infer about a person, given that the classifier predicted that you're going to go on to reoffend, what you can infer about their true label should be the same, independent of what their group is. Again, this is something that you might reasonably want. Okay, and so these two groups were talking past each other. ProPublica said your classifier is not fair because it doesn't satisfy the false positive rate condition. North Point said that your classifier is fair, that the classifier is fair because it satisfies the equal positive predictive value condition. And there's also another condition you can reasonably ask for, which is that the false negative rates be equal, right? That, conditioned on, if we look at the fraction of mistakes that the classifier makes on people who actually do go on to commit crimes, so, right, the fraction of people who actually do go on to commit crimes, but the classifier mistakenly predicts will not go on to commit crimes, that those should be equal. And ProPublica also noticed that the false negative rate was much higher for the white population than for the black population. And again, this is the direction of mistakes that is helpful for the inmate, right? Because if you are mistakenly labeled as low risk, then it's more likely that you will be released, right? So ProPublica observed that the mistakes in the harmful direction were made disproportionately on the African American population, and the mistakes in the helpful direction were made disproportionately on the white population. So these are all reasonable conditions. Maybe we can try to ask for all of these to be satisfied. And let me just sort of walk through why these are reasonable conditions, and then we can think about what is achievable and what is not. So what does it mean, right, that we should equalize positive predictive value across populations? Let's imagine that there's two populations, red and blue. So what would happen if we didn't equalize positive predictive value and the positive predictive value was, say, higher for the red population than for the blue population? Well, what would that mean? It would mean that your estimate that I am going to commit a crime, if I am labeled high risk, right, the probability that I will commit a crime, given that the classifier labels me as high risk, if I am from the red population, will be higher than your estimate that I will commit a crime given that I was labeled high risk if I come from the blue population. Right? If the positive predictive values are not equal, then when interpreting the signals that you get from the classifier, you really should take into account my race. And so it would be, like rational to release blue people when they get, or to not release blue people. It would be, let me just get these straight. It would be reasonable to release blue people when they receive a score of high risk, but not release red people when they receive a score of high risk, because if the positive predictive values are not equal, then when the classifier labels someone as high risk, it really means that they're higher risk if they come from the red population compared to if they come from the blue population. So if we don't equalize positive predictive value, we are explicitly incentivizing downstream decision makers to take race into account explicitly when they make their decisions. And similarly, if we do equalize positive predictive value, then rational decision makers shouldn't take race into account when they make their decisions, and we might like that they not take race into account. That's a good reason for wanting our tools to have equal positive predictive value across populations. Okay. And why should we want our classifiers to equalize false positive rates across populations? Well, if you are incorrectly labeled as high risk, then the classifier, this mistake of the classifier has actively harmed you, right? Because you are a low risk person, you're not going to go on to commit a crime if you're released. But if you are mistakenly labeled as high risk, this makes it less likely that you are going to be released on parole. And so the false positives are sort of the people that the mistakes of the classifier are harming. And so the false positive rate within a population is the probability that you will be harmed by one of these mistakes of the classifier if you imagine yourself as being born as a uniformly random low-risk member of the population. Okay, so if we imagine that, we've got two populations represented by the, circle on the left and the circle on the right, and everyone within these circles is low risk, and you are going to be born as a uniformly random low risk person. But the red circles within these balls are the people who are mistakenly classified as high risk and therefore have come to harm as a result of the mistakes of our classifier. Then the false positive rate is your chance of being one of these people who are harmed by the mistakes of the classifier if you're born as a uniformly random person. And if the false positive rate is higher in one population compared to another, then all things being equal, you would prefer to be born into the population that has the lower false positive rate. If we equalize the false positive rates between populations, then you have no a priori preference between which of these two populations you're born into. If the only thing you're worried about is being harmed by the classifier. And so equalizing false positive rates sort of corresponds to this nice condition of indifference between what group you're born into, when you're behind the veil of ignorance before you're actually born. Let's see, there's a question. Even if rational decision makers would use race to interpret a model without equal positive predictive value, wouldn't they be able to essentially de-bias an incorrect model by doing that? That seems like a fixable problem, whereas a model without equal false positive rates doesn't seem like something a decision maker can de-bias through their interpretation. Good. So you're right that, well, I'm not quite sure what you mean by de-bias, but there's an important point here that if we care about like the actual outcomes, like whether someone is released on parole or not, as opposed to what predictions are made as sort of a preliminary step, to inform a human decision maker, then presumably we should care about things like the false positive rate on the actual decisions that are made, not on the sort of predictive tool. but it's not that you can easily de-bias the sort of binary decisions that come out of a classifier that don't have equal positive predictive value, because information is lost. If I gave you sort of a correct, if I give you a correct risk estimate for every person, then you could use that for whatever you like. But if I give you just a sort of binary outcome like high risk or low risk, then I've applied, my like actual risk estimate that I might have under the hood to some arbitrary threshold. And it's not that you can go back and recover the information. Another question. The idea is that we don't want humans to be responsible for debiasing because humans are theoretically biased, hence the motivation for the algorithm. I guess that wasn't a question, that was an answer. And but here the debiasing is purely statistical. If we know how different the positive predictive value is, we can just account for that statistically in a final judgment. So maybe I've already answered this. Certainly you can, certainly the human decision maker can go and, apply Bayes' rule and do whatever they like. We'll talk about this a bit more. None of this necessarily results in the outcome decisions having the properties that you want, but we'll talk about this at some length. Okay, other questions before I go on? Okay. Yeah, so unfortunately, there's a sort of basic impossibility result here, which is that there's no way to get ProPublica and North Point to sort of stop talking past each other, in that it is not possible to simultaneously satisfy both of their fairness desiderata. And so we're necessarily going to have to think about how to pick and choose amongst them. Okay, so let me tell you the impossibility result in English, and then we'll derive it. It's actually quite simple, and it follows from Bayes' rule. So it says that if the base rates differ between two populations, that's just the sort of, the base rate in this context is just the underlying crime rate, the underlying prevalence of crime. What fraction of people in each population actually go on, for example, to reoffend when they're released? If the base rates are different between two populations, then there is no non-trivial classifier that can simultaneously equalize false positive rates, false negative rates, and positive predictive value across populations, unless that classifier is somehow able to perfectly make predictions. Okay, so we're gonna derive this, and it'll be a little bit clearer what it means when we sort of see it mathematically instead of in English. But the fundamental point here is that unless you are in one of the following two unrealistic situations, where either your two populations are identical when it comes to whatever statistic you're trying to predict, and populations are different, you never have identical populations, or unless you are able to perfectly make predictions, which again is unrealistic. Whenever there's any statistical uncertainty at all, you're going to make some kinds of mistakes. It turns out to be impossible to equalize false positive rates, false negative rates, and positive predictive value across groups. And so you're necessarily going to have to give up on one or more of these. And we're going to need to figure out some reasonable way to decide which of these conditions we want and which ones we're willing to give up on. Okay, so this is not a complicated result. We're gonna observe it in a couple of slides, but it's somehow an eye-opening result. It sort of says, okay, well, what does it mean for a decision-making process to be fair? Well, there's multiple reasonable things you might want a fair decision-making process to satisfy. We sort of argued why you might want a fair decision-making process to equalize false positive and false negative rates. We argued why you might want a statistical prediction tool to equalize positive predictive value. And this is saying, okay, well, too bad. Like, you're going to have to satisfy some of these, but not all of them. Okay, and this, by the way, has nothing to do with algorithms. This is just some basic fact about about decision making, it's equally true of human decision makers. Okay. All right. So let's figure out why this is true. It's actually a pretty simple fact, and maybe it's helpful sort of to stare for a moment at what is sometimes called the confusion table of a classification tool. And so the columns of this tool correspond to ground truth. So for every person, they will be observed either to have committed a crime or not. And for every person, they will have been predicted as high risk or low risk, which means they will fall into one of these 4 buckets, which are basically just going to represent counts of the number of people of each type. Okay, so if you were predicted as high risk and the tool was right, that's a true positive. If you were predicted as high risk, but the tool made a mistake, that's a false positive. If you were predicted as low risk and the tool was right, that's a true negative. And if you were predicted as low risk, but the tool made a mistake, that's a false negative. Okay, so false positives are mistakes made in the harmful direction. False negatives are mistakes made in the helpful direction. And true positives and true negatives are correct predictions. Okay, and so let's just think about what positive predictive value is and sort of apply Bayes' rule, since positive predictive value is really about it's a conditional probability. Okay, so what is positive predictive value? Well, it's just the probability that you will commit a crime given that you've been labeled as high risk, right? It's something about the statistical strength of the signal. If I say that someone is high risk, it's the probability that they will commit a crime given that they've been labeled as high risk. And we all learned Bayes' rule in kindergarten. Whenever you encounter a conditional probability like this, you should apply Bayes' rule and try to figure out what we can learn about it to see if it's something more interpretable. And so if we want to know what's the probability of crime given that you've been labeled as high risk, we can figure that out by computing the probability that you're labeled as high risk given that you've committed a crime times the probability that you've committed a crime divided by the probability that you are high risk. Okay, this is Bayes' rule. It should be familiar to all of you. And all of these things are quantities that we can get our hands on. So what's the probability that you've committed a crime? Well, that's by definition just the base rate. Let's call that P. Okay, so the probability that you've committed a crime, knowing nothing else about you, that's just the base rate in your population. What's the probability that you're labeled as high risk given that you've committed a crime? Well, that's just the fraction of true positives, right? People who are labeled as high risk and have committed crimes amongst all of the people who've committed crimes. So the fraction of people in the crime column who are labeled as false negatives, that's the false negative rate. And the true positive rate, the probability that you're labeled as high risk given that you've committed a crime, is just 1 minus the false negative rate. So the numerator here is just 1 minus the false negative rate times the base rate. And finally, we have to figure out the denominator. Well, what's the probability that you're labeled as high risk? Well, there's 2 ways that could happen. Okay, you could have been someone who actually committed a crime. That happens with probability equal to the base rate. And if you are someone who's actually committed a crime, then you will be correctly labeled as high risk with probability equal to the true positive rate, or in other words, with probability equal to 1 minus the false negative rate. Alternately, you might be labeled as high risk by being born as someone who did not commit a crime. This happens with probability 1 minus P. But then you're unfortunately labeled incorrectly as high risk, which happens with probability equal to the false positive rate. Okay, so this is just the definition of positive predictive value, but expanded out using Bayes' rule. And so suppose I've got 2 groups, a red group and a blue group. And suppose I've told you that the false positive rates are equal across these 2 groups and the false negative rates are equal across these 2 groups. We want to ask, well, when can it be that the positive predictive value is also equal across these 2 groups? Well, we just derived this expression for positive predictive value. It looks like this. I can write it out for the red group and for the blue group. And remember, we've assumed that the false negative rates are the same across the two groups and the false positive rates are the same across the two groups. So I'll just write that in black because those quantities don't differ on the left-hand side and the right-hand side. But the base rates might differ, and so that's something that might cause the positive predictive value to deviate between the two groups, even though the false positive rates and the false negative rates are the same. And so, now we just have this equation, right? When can it be that the left-hand side is equal to the right-hand side? And I claim there's only 3 ways it can happen. So first, of course, it can be that the base rates are identical. If the red base rate is equal to the blue base rate, then everything on the left-hand side is identical to everything on the right-hand side, and these two quantities are the same value. Or it could be that we have a perfect classifier, right? Maybe the classifier makes no mistakes at all. So the false negative rate and the false positive rate are both 0, right? And so then the numerator here is P, the base rate, but the false positive rate is 0, right? The false negative rate is 0, so the numerator is 1 times P, just P. The false positive rate is 0, so the denominator is also just 1 times P. And this ratio is 1, even if the base rates aren't different. The positive predictive value is 1 for both populations. And the only other way it can happen is that the classifier is trivial, meaning the false negative rate is 1 and the positive predictive value is 0. This will happen if the classifier just says everybody is low risk, right? Like, the classifier is just not going to be informative at all. In that case, it can also be that the left-hand side is equal to the right-hand side because the positive predictive value on both sides will just evaluate to 0. And those are the only 3 cases. And in fact, if you wanted to ask also that this classifier equalized not just positive predictive value, but negative predictive value, then you'd even rule out the trivial case as well. And you'd find that the only 2 instances in which you could equalize all 3 of these statistics were those in which you had the ability to make perfect predictions, which never happens, or if the base rates were equal, which could happen, but happens to be unusual because you really need them to be exactly equal. Okay. And so this impossibility result, it's not a deep mathematical fact, right? It's just Bayes' rule, but it does sort of bind our hands a little bit. It sort of says, okay, like, if we go through this ProPublica case study, the answer cannot be to design a new classifier that satisfies everybody, that equalizes false positive rates, false negative rates, right? That's what you'd need to do to satisfy ProPublica, and equalizes positive predictive value. That's what you'd want to do to satisfy North Point. We're going to have to somehow choose amongst these. Are there questions about that impossibility result before we go on? It's sort of interesting, but not mathematically complicated. Okay. There are other ways you could think about fairness, by the way. Like, everything we've talked about so far is what you might call a statistical notion of fairness. It computes some outcome statistic, some statistic of the confusion matrix, and it asks that this statistic be equalized across populations. But you could also think about fairness procedurally. Maybe to be fair, what we should really do is subject everyone to the same process. So for example, like maybe in an ideal world, what we would do is we would hold a trial, learn everything there is to know about an individual. We'd gather all information that was statistically relevant to the thing we were trying to predict. If we were perfect Bayesians, we would incorporate all of this information into some posterior belief that the individual is going to go out and commit a crime. And we should just be consistent. We should release exactly those people whose posterior risk, after we've incorporated all information, falls below some uniform threshold. And this threshold should be the same for everybody. Like maybe after I learn everything there is to know about you, if I think that there's less than a 50% chance that you're going to go on to commit a crime, I should release you. If I think there's more than a 50% chance that you're going to go on to commit a crime, I shouldn't release you. And maybe just doing this would be fair because it's the same process for everybody. There's another sort of nice thing about this, which is that this is also the Bayes optimal classifier. Like, if I don't care about fairness at all, I just care about making as few mistakes in my predictions, then this is exactly what I should do, right? Like, I should exactly, I should of course gather as much information as I can to make as informed a prediction as possible. And I should predict that someone will not go on to reoffend if my posterior belief that they will do so is below 50%. And I should predict that they will go on to reoffend if I predict that if my posterior belief that they will go on to reoffend is greater than 50%. So if I think that subjecting everyone to the same uniform procedure is fair, then I'm in luck, because this is also the Bayes optimal procedure that I should go through to minimize prediction error. Another question. Is there some kind of way to approximately equate positive predictive value and false positive rate? Like, if the base rates are within epsilon of each other, then we can get positive predictive value, false positive rate to be within delta of each other. So these impossibility results still continue to hold, with approximation. Now, of course, these quantities are mostly continuous. So, you can go back to the Bayes rule calculation and compute these epsilon and delta bounds if you want. But let's just say they don't degrade super gracefully. So, there are some things to be said about approximation, but to get sort of like non-trivial approximation, you'd really want the base rates to be quite close. But of course, you can get something if they're sufficiently close. Okay, so if you think about this as procedural fairness, then on the one hand you're in luck because then there's no tension at all between fairness and prediction accuracy. This is just the Bayes optimal classifier. On the other hand, in general, again, when base rates are different, this will not satisfy any of the statistical notions of fairness we've talked about. So applying this sort of uniform threshold on posterior belief will not in general equalize false positive rates or false negative rates or positive predictive value. So again, there's this is some other way you might think about fairness, but thinking about fairness in this way is inconsistent with asking for any of these statistical notions of fairness that we've talked about. And so once again, you somehow can't have it all. You've got to sort of commit yourself to a particular notion of fairness and ask if you can achieve that. So, okay, so I mean, there's a whole literature, there's a whole growing and enormous literature of people thinking about how to achieve various of these fairness desiderata, like even if you pick and choose, like say I want to equalize false positive rates, like how should I design machine learning algorithms that maximize accuracy subject to false positive rate constraints. There's an enormous literature where people try to do things like that and defend these different fairness desiderata on normative grounds. But what I want to ask in this class is, is there anything that game theory can tell us about how we might choose amongst these different incompatible fairness desiderata? And so one approach, okay, the one I'll go through in this talk, is to first write down some simple model for how people might respond to policy changes. Because in the end, the kinds of things we're trying to predict, right? Crime, for example, but you could imagine applying models like this to lending decisions. Will someone default or not? These are the result of individual human decision makers, and the things that we're talking about doing, imposing various fairness constraints on classifiers that, for example, will determine how our criminal justice system punishes people, or that will determine who gets loans. Well, these are, of course, going to be decision relevant policy changes that people might react to. And so we might write down a game theoretic model in which we imagine that people are rational actors and are going to change their behavior as a function of the policy decisions that we make. And then we could choose a goal within this model. Okay, there's different things we could ask for, but we could try to pick some societal goal. And then we could ask, okay, if here's our model, maybe you buy the model, maybe you don't, but within the model, here's our goal. We can start to ask, okay, well, do these various fairness desiderata help or hurt in achieving our goal? Maybe some of these fairness desiderata are actually compatible with the social goal that we're trying to achieve, and some of them aren't. Okay, so rather than trying to think normatively about these constraints myopically, would it be a good thing or not for the world if classifiers had equal positive predictive value, or if they had equal false positive rates, or if we followed this same Bayesian procedure for everybody, we can start to think about the effects, the equilibrium effects that will result from deploying classifiers that have properties like this, and ask whether those effects are good or bad. Okay, so I'm going to sort of briefly walk you through a case study trying to do just this. It's from a paper that I wrote with a bunch of Penn colleagues, fair prediction with endogenous behavior. If you're into this kind of thing, these slides are online, and if you click on the title, it'll take you to the paper. And this is joint work with a bunch of folks at Penn, Chris and Changhua, who are graduate students in the CS department and the econ department, respectively. Sampath, who many of you will know, he's in the CS department. Ricky, who's in the econ department, and Malash Pai, who until recently had been at Penn, but is now at Rice. Okay. So let me tell you what we do. I'll start by telling you what our model is. First, I'll give you a bird's eye view of the model, and then I'll, on the next slide, define it precisely. And I'm going to describe for you an extremely simple baseline model. Basically, I want to make the model as simple as possible so that you can sort of see why the results that I'm going to claim are true. And then at the end, I'll sort of mention ways in which you can stress test the model, ways in which you can complicate the model, try to make it more realistic in various ways, and see whether the main results break or don't break when you complicate the model in these various ways. And so this model will have a couple of moving parts. And maybe the most basic premise of this model, and I'm gonna talk about this model using the language of criminal justice, just because we've been talking about the ProPublica case study, but you'll see the model's simple enough that it's not really tied to any particular application. But the sort of basic premise of this model is that people are rational decision makers, and they're going to make decisions that are best for them, that maximize their own utility. Okay, so in this case, the decisions they're going to make are whether to commit crimes or not. And so individuals will weigh their legal opportunities, right? So you could decide not to commit a crime and go try to make money in some legal way. You'll weigh your legal opportunities with the payoff of committing crime. If you commit a crime, there's some payoff for that as well. But you're also going to weigh those payoffs with the chance of getting caught. You'll have some some disincentive, some cost to pay if you're caught and are sent to jail. And we'll talk in a moment about exactly how you would make this decision and how it relates to sort of the criminal justice policy that is set. But sort of the most basic premise of the model is that people are going to be rational decision makers. And so it doesn't make sense in our model to talk about like the base rate of a population without talking about a particular equilibrium. Like the base rate, the crime rate within a population will depend in aggregate on the choices that everyone in that population makes. Okay? Now, after you make your decision about whether to commit a crime or not, this will lead to the generation of some noisy signal. So think about this as evidence, some noisy signal about whether you've committed the crime or not. And it's noisy because, you know, we're not going to be able to just like deterministically make correct predictions about people. You know, it will be possible to commit a crime and get away with it just by luck. And it'll also be possible to be falsely accused. You know, you might end up in jail even though you actually didn't commit a crime. And as we said, as people make these decisions in aggregate, you know, in aggregate, this will determine the base rates in different populations, the crime rates. But the sort of the main thing that we're doing here, and that we're, to use an econ word, endogenizing, is these crime rates. These are quantities that exist only in equilibrium. Okay. And so, you know, that's sort of one of the moving parts, the people. But the other moving part and the other sort of half of the equilibrium is the criminal justice system that's going to make incarceration decisions, who goes to jail and who doesn't. And the criminal justice system will observe everything there is to observe in this model about an individual, which is what group they come from, what population they come from, and the evidence of their guilt, which is in this case the noisy signal that was generated as a function of their choice. And it'll somehow decide as a function of this evidence whether to punish them or not, whether to send them to jail, for example. And this is the thing that as mechanism designers we get to play with, and our goal will be to figure out what characteristics of the policy that we get to set in the criminal justice system will be relevant for goals that we might care about achieving. Okay, and so you know, these two moving parts are related to one another. In particular, the policy decisions we make about how exactly to turn evidence into decisions of who goes to jail or not will affect the incentives of the people who are deciding whether or not to commit crimes, and therefore will affect the base rates. Okay. And I mentioned already that people will make decisions as a function of their legal opportunities. So different people will be different insofar as they might have access to different legal opportunities. And the only way I'm going to model populations as differing is in their access to legal opportunities. So populations will have their, we'll call it their outside option value, but think about this as their access to legal opportunity. Their outside option value will be drawn from some distribution, and that distribution will potentially be different for different populations. And that's what's going to drive in our model the fact that we will sometimes get base rates that are different. Okay, so this is the model at a sort of 10,000 foot view. None of this is formal. I'll give you the formal specification on the next slide, but are there any questions about at least the high level premise at this point? Okay. So let's now dive into the model in a little bit more detail. Okay, so we'll have individuals I, and individuals will come from some group G, and the group will be relevant in two ways. So first of all, the group will determine the distribution from which your outside option value is drawn. So you'll have some outside option value. Think about this as your, the income that you can earn from some legal opportunity. And this is going to be drawn at random from some distribution that is sort of specific to your group. So different groups might have different access to legal opportunities. And because of this, it could be that group membership is actually statistically informative for predicting crime because it tells me something about what your access to legal opportunities are. Now, the individuals in this interaction are going to have a choice. It's going to be a binary choice. They're going to commit crime or not. We'll call that, taking action C or action N. And then as a function of the action you take, either committing a crime or not, they will generate a noisy signal. Okay, so some like real valued signal that will be drawn from a distribution that depends on whether they committed a crime or not. Okay, and so think about these signals as sort of the accumulated evidence of your guilt. And we're not going to really assume anything about these signal distributions. But imagine that sort of higher signals, correspond to stronger evidence of guilt. So if I see a really big number for your signal, that gives me stronger evidence that you're guilty. And so let's just imagine that higher signals are going to be more likely from the crime signal distribution compared to the no crime signal distribution. Okay, so you can like encode all sorts of things here, right? Like, you could imagine that there's the possibility that you're caught red-handed. There's like a video camera recording you doing the crime that would correspond to some really high signal. But you could also imagine that there's, less reliable evidence that corresponds to a lower signal. And there's the potential here that you could be falsely convicted. It might be that, due to bad luck, you get a relatively high signal even though you didn't commit the crime. And it might be that due to good luck, even though you did commit a crime, you get away with it because your signal is low. Okay. And then there's the adjudicator, sort of the implementation of the criminal justice policy. And the adjudicator observes everything there is to observe. He observes an individual's group. He observes the signal generated by the individual. Of course, he doesn't observe directly whether the individual committed a crime or not. And then he can decide whether to incarcerate the individual or not. And he can really do this in some arbitrary way. We will just encapsulate his decision-making process by saying that someone with signal SI from group G will be incarcerated with some probability F of G and SI. Okay, so this is like the object that potentially we get to design and ask questions about, how our choices in this function F affect what the equilibrium looks like. But for example, you could imagine that a natural choice of F just subjects the signal to a threshold. Like maybe I'll send you to jail if your signal is above some threshold and I won't otherwise. And it's within my design space to set potentially different thresholds for different groups. Okay, so I don't have to, but I could imagine setting thresholds differently for different groups, or I could set them the same, or I could do something more complicated. Okay, now, once I set the incarceration rule, this is going to feed back into individuals' decisions of whether they want to commit crimes or not. Because once I set the incarceration rule, this determines what your chance of going to jail is as a function of your actions. So for example, I can talk about the true positive rate of my incarceration rule. That is just the probability that you go to jail given that you commit the crime. Okay, it's just the expectation of this function f of gs when s is drawn from the crime signal distribution. And I can also talk about the false positive rate. That's the probability that you end up going to jail given that you don't commit the crime, which is again just the expected value of this incarceration rule function given that the signal is drawn from the no crime distribution. Okay, so once I fix the incarceration rule, now individuals can start to reason about, okay, like what's the chance that I'm going to go to jail if I commit the crime versus if I do not? And I'm going to model individuals as just pure expectation maximizers here. So what an individual is going to do is they're going to compute their expected utility for not committing a crime. They're going to compute their expected utility for committing a crime. And then they're just going to do whichever has higher utility. Okay, so if you don't commit the crime, what's your value? What's your utility? Well, you get your outside option value, VI, that's specific to you. I'm going to imagine that everyone has some cost for incarceration, some disutility that you'll get if you get sent to jail. So that's C. and also some payoff R if you commit the crime. Okay, so if you don't commit the crime, you get value VI, your outside option value for legal employment. Now, there's still some chance that you end up being punished that corresponds to the false positive rate of the incarceration rule. And so you still experience an expectation, this disutility, which is equal to C times the false positive rate. On the other hand, if you do commit the crime, then you get some payoff R. This is your reward for committing the crime. But now you have some presumably higher cost of going to jail, which is the true positive rate of the incarceration rule. And so you have to subtract off from your expected utility this potentially larger value, C times the true positive rate of the classifier. Okay, and so people will decide to commit the crime exactly when their expected utility for committing the crime is higher than their expected utility for not committing the crime. Okay, so very simple. And so we can see that we can sort of see how things feed back into each other. Once I fix an incarceration rule, that will determine how everyone makes their decisions, which will in turn feed back into a base rate for each group. Okay, so that's the model. We can now talk about what we might want to achieve within the model and how we might do it. But are there questions about the model and how these moving pieces interact with one another? Okay. So we have a simple model, and we're gonna set out a simple goal. You could write down other goals. Here's ours. We're just gonna ask, what criminal justice policy, what function F should we commit to if our goal is to minimize overall crime, right? And note that because crime rates are now a function of the policy that the adjudicator commits to, they're not fixed. So it's sensible to ask for the policy that minimizes crime. And so our question is going to be, okay, how should we design this function F if our goal is to minimize crime? And in particular, like if that's our goal, should we ask that our function F satisfies any of the fairness criteria that we've talked about, equalizing false positive rates and false negative rates, equalizing positive predictive value, applying this uniform threshold on Bayesian inference, or maybe something else. And note, by the way, that like in our simple model, everything we've discussed so far is implementable, right? Doing any of these things are at least options. We don't know if they're good options yet, but they're at least options. So for example, if we wanted this sort of procedural equality if we wanted to sort of basically apply Bayes' rule and compute for every individual their posterior probability of crime and just subject every individual to a fixed threshold, we could do that, right? Like we could condition on everything we know about an individual, which is in this case their signal and their group. We could compute a posterior belief that the action they took was to commit crime, and we could incarcerate them exactly when their probability of committing the crime, conditioned on everything we knew about them, exceeded some fixed group independent threshold. Okay, so this is something we could do with the sort of caveat that these quantities are really only determined in equilibrium, because if I want to compute like what's my posterior belief that you committed a crime given your signal, I have to know what's my prior belief that you committed a crime, which is a function of the base rates, and the base rates of crime are defined only in equilibrium. So it would be like a slightly tricky calculation to figure out what exactly is the incarceration rule that ends up applying Bayes' rule and submitting everyone to a fixed threshold, but it's like totally implementable within the model. Okay, and note, by the way, that because the outside option distributions differ, for almost anything we do, the base rates within the groups will differ, right? Because people's access to opportunity, legal opportunity, is a crucial piece of their decision for whether to commit crime or not. And because the outside option distributions differ, the base rates will typically differ. And so group membership will be statistically informative. And so if we do this, if we sort of try to apply an equal threshold to our posterior beliefs that someone's committed a crime, we will end up with some incarceration rule that depends explicitly on group membership. Okay. Or we could, just separately set thresholds on signals. We could say, okay, I'm going to incarcerate people from group G if their signal exceeds tau G, and I could slide these signals back and forth and stop exactly when I have equalized whatever quantity I care about. So I could equalize false negative rates or false positive rates or positive predictive value. So this is just to say that we've written down a rich enough model to interrogate all of the fairness desiderata that we've talked about, and we can ask in this model if any of them are any good. Okay, and so what I want to ask is, are any of these, which, if any of these fairness desiderata are consistent with the goal of minimizing crime? And so, let's just think about in this model, like what should we do if we want to minimize crime? Right, let's remember how individuals are going to make decisions. Right, they're expectation maximizers. They're going to choose to commit crimes exactly when their expected benefit for committing the crime exceeds their expected benefit for not committing the crime. Okay, and we don't get to control most of these numbers. We don't get to control what their outside option value is. We don't get to control their disutility for incarceration. We don't get to control their immediate benefit for committing the crime. The thing that we get to control is we get to control the criminal justice policy, which will in particular affect the chance that they go to jail if they commit the crime and if they don't. So, right, just like rearranging this, right, an individual I will commit a crime exactly when his value is less than this expression. His outside option value should be less than his value for committing a crime plus his disutility for being incarcerated times the difference between the probability that he'll be incarcerated if he doesn't commit the crime compared to if he does. Okay? And right, the people who commit the crimes will be exactly those people whose value is less than this expression. And so the crime rate will be exactly the probability that a random person from the population G, right, a random person who has their valuation drawn from outside option distribution DG, has a valuation V that makes it worth their while to commit a crime. Okay, so we can write down as a function of the false positive rate and of the true positive rate of the classifier that we end up deploying what the crime rate is going to be in each of these populations. And note, by the way, that we want to minimize overall crime, but there's no interaction here between the crime rates in one population or another, because we haven't asked for, we haven't insisted that this function should be independent of G, that it should be the same for every group. So in principle, we have the ability to set the incarceration rule independently for each group. And so minimizing overall crime, we won't have to make any compromises here. We can sort of individually for each group choose the policy that minimizes crime within that group. Okay, and so we can sort of say, okay, here's the crime rate. It's the probability that a random person from group G has an outside option value that is, less than this critical threshold. We can't control R or C, but we can control the false positive rate and the true positive rate of this classifier here. If we want to minimize the chance that the outside option value of a random individual is below this threshold on the right-hand side, what we want to do is we want to minimize the right-hand side. Or equivalently, the thing that we want to do is we want to maximize the disincentive for committing crime. We want to maximize this quantity delta G, which is just the difference between the true positive rate on population G and the false positive rate. Right, this is your disincentive for committing crime, because it's the difference in probability that you are punished if you do commit the crime compared to if you don't. And we can observe that the true positive rate and the false positive rate on a population are a function of the signal distribution, right? The probability that you are incarcerated if you commit the crime compared to if you don't. But both of these expressions are entirely independent of the outside option distribution, right? We can just sort of look at these things, and the false positive rate and the true positive rate of the classifier depend on the action that you take, but they don't depend on the outside option distribution of your population. And what we can learn from that is that although we have the ability to set this incarceration rule differently for different groups, we shouldn't, because identically for each group, the thing that we want to do is we want to choose the incarceration rule that maximizes the disincentive for committing crime, and doing that happens to be independent of the outside option distribution of that group, which is the only thing that differs between groups. So, who knows what the optimal policy will look like? It'll depend on what these distributions look like. But what we can learn right away is that the optimal policy will not make distinctions based on group. It will interpret signals and map those signals to incarceration rules identically, independently of the individual's group. Okay, so what we know is that the optimal policy will have the same incarceration probability as a function of the signal, no matter what group you come from. And so if I look at the false negative rate on a population, or if I look at the false positive rate on a population, again, what those are, they depend on the incarceration rule for that population, but those are the same across populations. They depend on the signal distribution, whether you've committed a crime or not, but again, those are the same across populations. They turn out not to depend on the outside option distribution. And so the optimal policy, the one we pick for minimizing crime within this model, will happen to equalize false positive rates and false negative rates across populations, even though we didn't set out to sort of solve a problem that explicitly asked for that as a fairness desideratum. We just asked for the policy that would optimize our population-wide goal, in this case to minimize crime. And what we found was that the policy that does that happens to satisfy at least one of these fairness desiderata, the one asking for equalized false positive and false negative rates. And of course, we can ask, does it satisfy the other fairness notions? And in general, it will not. Right? We can observe that. So first of all, if we set the same incarceration rule for all populations, then if the outside option distributions differ, the base rates are going to differ as well, right? The base rates were a function of the incarceration rule and of the outside option distributions. And so if the incarceration rule is the same across populations and the outside option distributions are different, the base rates will be different too. And of course, the optimal policy won't be perfect. These signals are noisy. It also won't be trivial. And so we already know from the impossibility result we proved earlier in the lecture that this optimal policy cannot equalize positive predictive value. And it's also not going to be sort of procedurally fair in the sense that it will not subject everyone to the same sort of risk threshold in making their decisions. Okay, and so to see this, let's make a simple observation. So in general, these incarceration rules could be complicated. They could map, they don't have to be deterministic. There could be probabilities of incarceration as a function of the signal. But one thing that's true is that if our signal distributions are satisfy the natural property that that higher signals always make it more likely that you've committed a crime, right? So if I look at the odds ratio of the signal, the probability of seeing that signal if you committed the crime compared to the probability if you didn't commit the crime. If this odds ratio is only increasing with the signal, this is the condition that sort of corresponds to saying that higher signals are more evidence of guilt. Then it's not too hard to see that the optimal policy will actually be some group independent threshold on the signal. That is, the optimal policy will fix some threshold tau, the same for every group. When it sees that you've got signal Si and that you're from group GI, it'll throw away the fact that you're from group GI. That won't be relevant, and it'll just send you to jail exactly when your signal is above some threshold. But that will not correspond to applying some equal threshold to the posterior. Right? Applying an equal threshold to the signal will typically correspond to applying a group-dependent threshold to your posterior probability of crime. And again, this sort of follows by Bayes' rule, right? If I look at the probability that you've committed a crime conditioned on your group and the signal, that's just the probability of the signal conditioned on the fact that you've committed a crime and your group times the probability that you've committed a crime given your group divided by the probability of the signal given your group. And we can write out all of these quantities and observe that the probability of your signal given your group, that's independent of your group, because what signal you generate is a function only of whether you've committed the crime or not. The probability that you've committed a crime given your group, that's the base rate in your group. And we can compute the denominator as well, the probability that you've generated your signal. Well, it can happen in two ways. Either you committed the crime and your signal came from the crime distribution, or you didn't commit the crime and your signal came from the not crime distribution. But again, because in general, the base rates are not different, applying a group independent threshold on the signal will correspond to applying a group dependent threshold on the posterior beliefs. So if we look at our incarceration rule in this Bayesian way, if we imagine that what the adjudicator is doing is conditioning on everything they've observed, right, the group that an individual comes from as well as their signal, then what we see that he's doing is he's going to send people to jail if the posterior probability that they committed a crime exceeds some threshold that now depends on their group, right? Some people might need to, as a function of their group, make the adjudicator more confident that they've committed a crime in order to be sent to jail than other people. Okay, and so the optimal policy in this model will also not satisfy this sort of procedural fairness notion. Okay, and so now let me just take a moment to sort of reflect on like what we might have learned here. So first of all, in this model, at least, the optimal incarceration rule for minimizing crime intentionally ignores group membership, even though group membership is statistically informative for prediction, right? Like if we just cared about making as few mistakes as possible in our prediction, then we would use the Bayes optimal rule. We would condition on everything, including group membership, and we would subject everyone to the same threshold. We'd send you to jail if we thought it was better than even odds you'd committed a crime, and otherwise we'd release you. The optimal policy here doesn't do that. It's intentionally throwing away a statistically informative piece of information, which is group membership. Why is it doing that? Well, it's because group membership is statistically informative, but it's not under individual control. Right, like in this model, you can control whether you commit a crime or not. So you have some control over what signal distribution your signal comes from, but you can't choose to have been born into another group. Right, the base rate is like different across groups. That's why group membership is statistically informative, but you have no control over the base rate in your group. You have no control over what group you were born into. The only thing you can control is whether you commit the crime or not. And so if we did the statistically optimal thing, if we conditioned on all of the statistically relevant information, because I would be making decisions in part using information like demographic information that is not under your control, it would distort incentives. Right? And so like saying that another way, if we applied an equal threshold to the posterior probability of crime when deciding whether to incarcerate you or not, this would result in having an unequal disincentive to commit crime across populations, right? Because we would be making our decisions in part on information that you have no control over. And this would result in innocent people from the group that happened to have the higher crime rate facing an increased probability of being falsely convicted, which would result in a diminished disincentive for them to break the law. And in this model, since it's a game theoretic model and people are making rational choices, minimizing the crime rate is all about correctly managing incentives, right? Like, we are intentionally making decisions that are suboptimal from a statistical point of view if we only wanted to make correct decisions, because we don't want to distort incentives by using information not under individual control. Okay, so this was a super simple model, and so whenever you're trying to learn something using like a game theoretic model, there's this trade-off, right? Like you can write down a simpler model, but which gives you sort of crisper predictions, but it's less reflective of reality, or you can write down a complicated model, which hopefully is more reflective of reality, but maybe has less crisp predictions. But it's important to check, when you've written down a simple model, that it's not super brittle. Like, ideally, the insights we got from this model wouldn't totally break down if we tweak the model in various ways. And so let me just mention a few ways you could tweak it. So we sort of assumed in the talk, for simplicity, that these numbers C and R, the cost for incarceration and the reward for committing crime, were just these like fixed constants, but you can actually have those also vary by individual. They can be drawn from arbitrary distributions that depend on the groups. Nothing changes. We also assumed everyone was fully rational, that everyone was just an expectation maximizer. You can also mix into the population people who are irrational. They're just going to pick random actions, or they'll always commit crimes, or they'll never commit crimes. That doesn't change anything. We assumed that signals, these signals were identically observed. Of course, some populations are policed more than other populations, and so signals aren't identically observed. You can sort of complicate the game a bit by designing into it like a third party that you could call the police, that will have their own incentives and get to decide the frequency with which they will inspect individuals from different groups. Their goal will be to just maximize their chance of discovering crime. And in this model, incarceration happens only if your signal is observed and then crosses the threshold for incarceration. This doesn't change anything. And finally, what is important is we assumed that the signal distribution depends on your action, but not on your group. But of course, if we make the signal distribution different for different groups, then the results can change. Okay, so in summary, there's many possible notions of fairness. It's possible normatively to make a case for each of them, but unfortunately, they're mutually incompatible with one another. A game theoretic model might help in choosing amongst them, at least if you buy the assumptions of the model. And the assumptions of the model at a high level of our model is that, one, individual decisions are actually rationally responsive to policy, that if you change the criminal justice system, it'll change people's decisions about whether to commit crime or not, and that the signals observed by the adjudicator are conditionally independent of group, that they only depend on your individual decision. And what we learn is that if you buy those assumptions, then equalizing false positive and false negative rates is consistent and in fact necessary for minimizing crime, and the other notions of fairness are not. And so therefore, if you observe that in deployed systems, false positive rates and false negative rates are not equal, then either current policy is suboptimal for the goal of minimizing crime, or one of the assumptions used to derive this result fails to hold. Okay, and you can use that to interrogate the assumptions. And in fact, if the assumptions hold, right, like if the assumptions fail to hold, like if the signals really do differ, not just by crime, but by group membership, then maybe that is itself undesirable and something to look into. All right. So with that, thank you. This was the last lecture of NETS 412, and it was a pleasure teaching you all. Good luck to everybody, and I hope you enjoy final exams and the rest of the summer, such as it is.